In this video, we're going to be going over last week's geometry topic, which was on congruent triangles and proofs involving congruent triangles. So just to review, two triangles are congruent when all of their corresponding sides are the same length and all of their corresponding angles are the same measure. In other words, they are exactly the same size and shape. So in the triangles below, we know that they are congruent. It says that. It tells us that the triangles are congruent. So let's write down what their corresponding parts will be. And you might want to take a second and pause the video and try to write down the corresponding parts on your own. Okay, so let's start with the sides, the corresponding sides. So if the triangles are congruent, side AB is going to correspond to side DE on this triangle. So we know that AB is congruent to DE. And we can double check that we're correct, that AB corresponds to DE by taking a look at the letters in the names of the triangle. AB is the first two letters here, so it will correspond to the first two letters over here, which is DE. Okay, moving on. BC corresponds to EF. Let's just double check. Second and third letters, all good to go. BC congruent to EF. And finally, side AC will correspond to side DF. Okay, now for the angles. So angle B corresponds to angle E. Second letter corresponds to second letter. Angle A corresponds to angle D. First letter corresponds to first letter. And angle C corresponds to angle F. Last letter corresponds to last letter. So it's a lot of work to show that all the corresponding sides and all the corresponding angles are congruent in order to prove two triangles congruent. So luckily, we have some shortcuts for proving triangles congruent. So here are the first three that you talked about in class. We'll do some practice with them on this video, and then we will talk about the remaining two. So we have side, 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 or SSS. In the two triangles, we have them congruent by SSS when there are three pairs of congruent corresponding sides. SAS, or side angle side, is when we have two pairs of congruent corresponding sides and the congruent angle in between the two sides. The order does matter, and the letters in the name tell us the order that we have to see the information in. So the angle, the A, does need to be directly in between the two sides. Notice here how the angle is directly in between the two sides. And then finally, we have ASA, angle, side, angle, side, angle, in that order with the side directly in between the two congruent pairs of angles. These are three methods of proving triangles congruent. Let's take a look at some examples. So in example number 1, we're given that angle A is congruent to angle D. We're given that angle B is congruent to angle E, and that side AB is congruent to side DE. So here, I see that the triangles are congruent to each other by angle, side, angle, side, angle. Notice how the congruent pair of sides is directly in between the two congruent pairs of angles. Moving along over here, we have WX congruent to XY. Let me mark that in my diagram. WZ congruent to ZY. And XZ is congruent to itself. If we didn't know that XZ was congruent to itself, remember how it's a side that's shared between the two triangles. So we would still know that it's congruent to itself by the reflexive postulate, even if that wasn't given to us. We could still conclude that due to the reflexive postulate, anything is congruent to itself. So definitely look out for that shared side between two triangles. It does come up a lot. So here we have 1, 2, 3 pairs of congruent sides. That's 3 S's for side, side, side. So these triangles are congruent by SSS. Next, we have RS congruent to TS, angle QSR congruent to angle TSU, and QS congruent to US. Notice that even if they didn't tell us that these two angles were congruent, we could conclude that they were congruent because these are vertical angles. They come out of the same point, formed by intersecting lines, and they look like they're across from each other. And vertical angles are always congruent. So here we have side, angle, side, side, angle, side. Notice how the congruent pair of angles is directly in between the two sides. Let's take a look at this first one over here. So we have two angles, one pair of angles, and one pair of sides. We want to write down another additional piece of information that we would need to know for SAS. So for SAS, the angle does need to be directly in between the two sides. So if I have side angle, the side would have to come after. Side angle, the side would have to come right after for side angle side, side angle side. So that would be JI congruent to TS. Over here, we have one pair of congruent corresponding sides. If you take a look at what else you can conclude here, notice that we have vertical angles, so they are always congruent. I'm going to put that into my diagram. So I'm going to write down so far angle UVW, that's this angle here, UVW. Be specific. Some people like to write angle V is congruent to angle V. That's not true. These are not the same angle. These are two separate angles and two different triangles. So angle UVW is congruent to angle KVM. And that's because they are vertical angles, so they are always congruent. So now we have side angle, side angle. We need one more S for side angle side, and it would have to come directly after the angle. Side angle side directly after, side angle side directly after. So that would be side WV congruent to side VM for side angle side, side angle side, with the angle directly in between the two pairs of congruent sides. Which of the following are congruent by SSS? Feel free to pause the video so that you can decide for yourself. This first pair of triangles is congruent by SSS. I'm going to put a check mark. 3 pairs of congruent corresponding sides. In the second pair, I see vertical angles, which are always congruent, so I'm going to mark that. So what I see here is 2 pairs of congruent sides with a congruent angle in between. Side, angle, side, side, angle, side. That's not SAS. I'm going to write down here, that's not SSS, that's SAS. So I'm going to write down here, no, an X mark. It is not SSS, it is SAS instead. Okay, here we have congruent right angles. So that's a pair of congruent angles. And we have a pair of congruent sides. Notice again the vertical angles, which are always congruent. So what we have here is ASA, ASA, not side angle side. Finally here, we have 2 pairs of congruent corresponding sides. And I notice that the 2 triangles share this side over here. Since it's shared, we can say it's congruent to itself by the reflexive property. So that gives us a third pair of congruent corresponding sides. So yes, these 2 triangles are also congruent by SSS. And finally, write down 3 congruent statements that would make the triangles congruent by ASA. The congruent right angles are already here, so I'm definitely going to use that as one of my pair of angles. Angle Q is congruent to angle M. I need another angle, and I need a side in between the 2 angles. Since the side needs to be in between the 2 angles, let me pick the other angle first. I can pick either angle R or angle P in this triangle, so I'll just pick angle R. And that corresponds to angle L in this triangle. So we have angle R congruent to angle L. Now I need the side that's in between the 2 angles, directly in between. So that would be this side here and this side here. So that's QR congruent to ML. ASA, ASA. Okay, let's figure out how these two triangles here are congruent to each other. So we have AD congruent to DC. BD bisects angle ADC. So angle ADC is being split into two equal parts. And notice we have the shared side between the two triangles, so it's congruent to itself by the reflexive property. So what we have here is SAS, SAS. Over here, we're given that angle B is congruent to angle D, and we're told that C is the midpoint of BD. If C is the midpoint of BD, it splits BD into two congruent parts. And then notice, we have vertical angles, which are always congruent. So we have ASA, ASA. To answer the questions here, it says, what kind of angles are angle B and angle D? Well, if I highlight these two sides over here and the transversal that intersects them, I can see that angle B and angle D are inside the lines on different sides of the transversal. You can see that letter Z. In the corners of our Z are our alternate interior angles. And since we do have congruent alternate interior angles, we can say that the lines forming them are parallel to each other. So we could make the statement that AB is parallel to DE because if alternate interior angles are congruent, the lines forming them are parallel. Over here, we have AD congruent to DC, and we know that BD bisects AC, means it splits it into two congruent parts. Notice the shared side between the two triangles, so it's congruent to itself by the reflexive property. So here we have side, 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 or SSS to prove these two triangles congruent. Finally, over here, we have parallel sides of the triangles. I'm going to first highlight these two parallel lines with the same parallel marking and the transversal that intersects them. Notice my letter Z, and in the corners, I have my alternate interior angles inside the lines on different sides of the transversal. And when parallel lines are cut by a transversal, alternate interior angles are congruent. Now I'm going to highlight my other two parallel lines and the transversal that intersects them. And notice how I have another pair of alternate interior angles inside the lines on different sides of the transversal. And then finally, I have the shared side of the two triangles in between the two angles. So what I have here is angle, side, angle, angle, side, angle. So always look out for parallel lines cut by a transversal. If the question tells you that lines are parallel, probably because you have parallel lines cut by a transversal. The most common kinds of angle relationships when you have parallel lines cut by a transversal are alternate interior angles. So take a look out for that Z shape. Highly recommend highlighting the parallel lines and the transversal so you can find those alternate interior angles. Another one that comes up a lot as well are corresponding angles. So those are two to make sure that you are familiar with. Okay, now we're actually going to write a proof. So here we know that AB is congruent to CB. We know that BD is a median of AC. So let's remind ourselves what a median is. A median is a triangle segment that connects a midpoint of a side to the opposite vertex. So we know that D is the midpoint of side AC since BD is a median. If D is the midpoint of side AC, it's splitting side AC into two congruent parts. And then we see the shared side between the two triangles, which is congruent to itself by the reflexive postulate. So we see here that we're going to ultimately prove that the two triangles here are congruent by SSS. Take a second and try to write the two-column statement reason chart by yourself. I'm going to display my statement reason chart here in about 1 second. So if you pause the video and take a look at the proof here, we have all the components that we mentioned out loud. It's definitely a good idea to mark your diagram first before you start writing the proof. So that way you can come up with a plan and make sure that all of the information that is in your plan ends up into your proof. I'm just going to double check that I mentioned everything needed for SSS. So we had one pair of congruent sides, AB and CB from the given. So that's 1S. And then after we said that D is the midpoint of AC, we knew it split it into two equal parts, giving us another pair of congruent sides of the two triangles. And then finally, our third pair of sides came from the shared side being congruent to itself. That was by the reflexive postulate. So I did mention everything needed for SSS. Always a good idea to make sure that everything that's in your diagram, everything that you came up with in your plan, makes its way into your proof. Here we have angle, angle, side. So for angle, angle, side, we need two pairs of congruent angles followed by a congruent side. So let's mark some information that would make these two triangles congruent by angle, angle, side. I'm going to mark angle A congruent to angle B. I just picked that. And I'll pick the vertical angles because they are always congruent to each other. So that's angle AED and angle CEB. And now to make AAS, we need the side following the two angles. So angle, angle, let's put the side here. Angle, angle, I'll put the side right here. So that's DE congruent to CE. And that's one set of information that would make these two triangles congruent by AAS. Two angles followed by a side, two angles followed by a side. We also have hypotenuse-leg theorem, or HL for short. And hypotenuse-leg theorem is specifically for right triangles. You can remember it's for right triangles because if you don't have a right triangle, you don't have a hypotenuse and you don't have a leg. Those are special parts of right triangles. Aside from just having a right triangle, you also need the H part and the L part. The H part is congruent hypotenuses. The hypotenuse is the part of the triangle directly across from the right angle, so those need to be congruent to each other. And you need one pair of congruent legs. The other two sides of a right triangle are called legs. So as long as one pair of legs is congruent, you have HL satisfied and you know the two triangles are congruent. Okay. So I want to also talk about two methods that do not prove triangles congruent. So one is SSA. You might remember in class, your teacher might have said that if you write it down the other way, it's a word that you really don't want to be writing down on your geometry test. So here I have an example of why SSA is not a valid way of proving triangles congruent. Here I have two triangles that have SSA satisfied. Congruent side, followed by congruent side, followed by congruent angle. But notice these two triangles are not exactly the same. They are quite different, even though they have two congruent sides followed by a congruent angle. So SSA doesn't always make congruent triangles. And if something doesn't always make congruent triangles, it's not one of our methods of proving triangles congruent because we want something that works in any situation, no matter what. So we are not going to use SSA. If you're tempted to use it, if you have the information for it, just remember what it is backwards and say, no, this is not a valid method of proving triangles congruent. AAA also does not work, or AA for short. If I give you an example of two equilateral triangles, all equilateral triangles have 60-degree angles because not only do they have three equal sides, but they also have three equal angles. But just like my pictures here, even though two triangles are equilateral and have the same angle measurements, they could clearly be different sizes, have different side lengths, and not be congruent to each other. So AAA doesn't prove triangles congruent in every single situation. So it is not one of our methods of proving triangles congruent. Okay, let's take a look. We have a proof over here. So we know that JL is an altitude of triangle MJK. If it's an altitude, that means it's a perpendicular line to the side of the triangle, which means it forms right angles with the side of the triangle. Perpendicular lines form right angles. L is the midpoint of MK. So it cuts the side MK into two congruent parts. We need to prove that triangle JML is congruent to triangle JKL. I also notice the shared side over here. You might be tempted to say that the two triangles are congruent by HL. But remember, besides just having right triangles, for HL, you need congruent hypotenuses and a pair of congruent legs. The hypotenuse is across from the 90-degree angle. And unfortunately here, we do not have any information about the hypotenuses. But that's okay, because from what we have here, we have SAS, SAS. And SAS also does prove the triangle's congruent. Try to write up all of this information that we marked in the diagram in a proof. I'm going to display a completed proof in about 1 second. So this proof ended up being a whole lot of steps. So just make sure that you have fully explained why all of your statements are true. So notice how before I could state that these are right angles, I first had to say how I knew that JL and MK were perpendicular to make those right angles. And the reason I knew that JL was perpendicular to MK is because JL was an altitude of the triangle, and an altitude is a perpendicular line in a triangle. Then, once I knew that the altitude was perpendicular to the side of the triangle, I could say that I have right angles since perpendicular lines form right angles. And then once I knew that these were both right angles, I could say that they were congruent because all right angles are congruent. They all have the same measurement. I also knew that ML was congruent to KL. That was because the midpoint cuts the line segment into two congruent parts. And I knew JL was congruent to itself by the reflexive postulate. So that gives me all my information for side, angle, side, side, angle, side. So the triangles are congruent by SAS. Here's another one. Let's take a look. So angle ADC and angle BDC are right angles. Let me put this right angle in the diagram. And they also tell us that AC is congruent to BC. I see a shared side between the triangles, so I'm going to mark it as congruent to itself. You might be thinking this is side angle side, but what I have here is side angle jump side. Side angle jump side. For side angle side, the side would need to be here for side angle side, side angle side, but we don't have that. But what we do have are right triangles. And if we have right triangles, HL is also a possibility. We do have congruent hypotenuses here. The hypotenuses are congruent. And we do have a pair of congruent legs. So HL can be used here. Take a second and try to write up a proof that proves these two triangles congruent by HL. So notice that before I can use HL, since HL is specifically for right triangles, in my proof, I do need to state that these two triangles, ADC and BDC, are right triangles. And my reason for that was if a triangle has a right angle, then it is a right triangle. Then after that, as long as I mention my congruent hypotenuses and my pair of congruent legs, I have everything I need for HL. Let's do one more really quickly. So PQ is parallel to DE. PB, so PB is right over here, is congruent to AE. And angle D is congruent to angle Q. We need to prove that these two triangles DEB and QPA are congruent to each other. So the first thing I see is that information AE and BP are longer than the sides of the triangle. What I really need to prove the triangle's congruent is BE, which is the side of this triangle, and AP, which is the side of this triangle. So in order to get those sides, we need to make the information that we were given smaller through the subtraction postulate. I also see that we have parallel lines cut by a transversal, and I see that we have alternate interior angles. So I see already I'm going to be proving these triangles congruent with angle, angle, side, angle, angle, side. All I need to do is use subtraction to get the sides that I need. So I'm going to pause the video. I'm going to write up the proof. Try to do it yourself as well. Notice in my proof that I mentioned my congruent alternate interior angles, and my reason for that was that alternate interior angles are congruent when parallel lines are cut by a transversal. Make sure that reason in your proof is complete and mentions that they're congruent, and it's because we have those parallel lines cut by a transversal. In order to get PA and BE, we need to take here PB and subtract off AB so we could be left over with PA. And on this side, we need to take AE and subtract off AB so we could be left over with BE. And PA and BE are the sides of the triangles that we want. This minus this is that. this minus this is that. That's substitution. And then we have angle, angle, side to prove the two triangles congruent to each other.